Space-time really changes. Lorentz contraction and the muon experiment. We saw that in a moving frame with proper time tau, the rate of time progression slows down, d tau less than dt. Special relativity brings yet another remarkable phenomenon. An object in motion appears contracted in the direction of travel when observed from a stationary frame. This is known as the Lorentz contraction. Let us confirm that this has been verified through real experiments. Lorentz contraction. Let us begin by setting up the framework for Lorentz contraction. We have two inertial frames. Frame S, observer A. The perspective of an observer watching the object move from outside the stationary frame. Frame S prime, observer B. The perspective moving together with the object at rest relative to the object. Definition of proper length, L naught. The length measured by an observer at rest relative to the object is called the proper length and serves as our reference. Let us first derive the proper length of the train from A's perspective. Observer A is standing on the platform. Train B approaches, carrying observer B. The positive x direction is the same for both frames. From B's perspective, B and the train are moving together. In other words, the train appears stationary to B. The length of the train, measured by B using a ruler, is defined as the proper length L naught. L naught equals x prime 2 minus x prime 1, where x prime 2 denotes the front end of the train, and x prime 1 denotes the rear end, which coincides with B's origin O prime. The length of the moving train as measured by observer A is L equals x2 minus x1. Here, an important condition must be satisfied. To measure the length of a moving object, observer A must record the positions of the front end and rear end at the same time. T1 equals T2 equals T. If either end is measured first, the object will have moved in the meantime, resulting in an inaccurate measurement. A measures the length of the train at the moment when the origins of A and B coincide. Now let us use the Lorentz transformation to express B's coordinate x prime in terms of A's coordinates x, t. Here we use the Lorentz transformation to express the proper length L0, measured in B's frame, in terms of A's coordinates. The calculation steps are shown on this screen, so please pause the video and work through each step at your own pace. We have derived the Lorentz contraction. This means that from the perspective of a stationary observer A, the length L of a moving object is shorter than its proper length L naught. As a simple example, let us set 1 over gamma equals 1/2. If the proper length L naught is 2, then L is observed to be half that value, namely 1. Why does this phenomenon occur? To uncover this mystery, let us now examine the situation from B's perspective using the equations. We begin by rewriting the Lorentz transformation as an equation for T. When observer A simultaneously measures the front end x2 and rear end x1 of the train, how does this appear in B's frame? In A's frame, the measurements are made at the same time. T1 equals T2 equals T, so T2 minus T1 equals 0. We now find the difference in the times at which B observes A's simultaneous measurements of the front and rear ends. What does this result tell us? The time interval that A measured simultaneously is not 0 in B's frame. Let us carefully unravel the reasons step by step. We consider the situation from B's perspective. Since there is no privileged inertial frame, from B's point of view, B is at rest the origin O prime, while A approaches moving in the negative x prime direction at constant velocity. How does A's simultaneity appear to be? Let us first examine the sequence of events experienced by each observer, scene by scene. A is approaching B, who is at rest, moving in the negative x prime direction. At this point, A has not yet measured the length of the train. A's origin O has now arrived at the front end x prime 2 of B's train. At this moment, B records the time. Time intervals are generally calculated as future T2 minus past T1, which gives a positive value. Therefore, the time coordinate at this moment in B's frame is T prime 1. Some time has elapsed in B's frame, and A's origin O has now reached the midpoint of the train. O prime equals x prime 1 and O have now coincided. At this moment, B records the time T prime 2. The time elapsed on B's clock is T prime 2 minus T prime 1 greater than 0. It is not 0. A claims to have measured the length of the train simultaneously at this moment when O prime equals O, T2 minus T1 equals 0. In other words, A's clock registered no elapsed time, yet both observers shared the same sequence of events. This gives rise to a puzzling phenomenon. No time passed for A, while time did pass for B. Now let us consider the length of the train as measured by A from B's perspective. A claims to have measured the length of the train at the moment when O prime equals O. If that were the case, the length of the train as measured by A should already be 0 at that moment. This is because at the instant, A arrives at B's origin O prime, the rear end x prime 1 of the train. The majority of the train is already past that point. However, this is only if we accept A's claim at face value, which is physically impossible. Let us now examine the situation of A's measurement from B's perspective. A began measuring at the moment of arriving at the front end, x prime 2 of the train at time t prime 1, and finished measuring at the moment when origin O prime equals x prime 1 and O coincided at time t prime 2. B's own time interval is t prime 2 minus t prime 1 greater than 0. However, since A is moving in the opposite direction to B, when we apply the Lorentz transformation to convert to A's coordinates, the sign of delta t prime is reversed and becomes negative. Therefore, we obtain delta t prime equals negative gamma VL over c squared. According to B, the reason why the proper length appears contracted in A's measurement is as follows. A began measuring at x prime 2. During the time until A reaches the rear end x prime 1, the rear end x prime 1 continues to approach A's origin O at velocity v. Therefore, B would argue that it is only natural that the length of the train is measured to be shorter. The two claims are completely different, so which one is correct? In fact, both are correct. We have previously stated that it is crucial to specify from whose perspective a physical phenomenon is being described, and from each observer's own perspective, this is an undeniable fact. This is known as the breakdown of simultaneity. An event that occurs simultaneously in one inertial frame is not simultaneous in another. This is one of the most important consequences of special relativity. We have repeatedly stated that there is no absolute time or absolute space, and this is yet another manifestation of that fact. We tend to forget this because we are so accustomed to our everyday intuitions. We have seen that objects contract and expand under Lorentz contraction. We have also already derived that the proper time of a moving object runs slower. In many explanations of special relativity, we often encounter expressions such as time appears to slow down or objects appear to contract. Let us examine whether these are merely appearances or whether time actually slows down and objects actually contract, using the muon experiment as our example. The muon experiment. Muons make up the majority of cosmic rays reaching the Earth's surface. Approximately one particle hits an area the size of a hand per second. They are generated at an altitude of approximately 10 kilometers in the atmosphere. The proper time, rest lifetime, of a muon has been confirmed in many experiments to be tau naught equals 2.2 times 10 to the minus 6 seconds. Muons approach the Earth's surface at 99.938% of the speed of light. Let us first calculate the distance a muon can travel from the perspective of a ground observer without using special relativity. Distance equals velocity times time. According to this result, the muon should decay after traveling approximately 659 meters. However, muons generated at an altitude of 10 kilometers are actually observed to reach the Earth's surface. Why is it that muons, which should only be able to travel 659 meters, are able to reach the Earth's surface 10 kilometers away? Let us investigate this mystery from two inertial frames: the perspective of the ground observer and the perspective of the muon itself. According to special relativity, the proper time of a moving observer as seen from a stationary frame is given by d tau equals dt over gamma. Setting tau naught equals t over gamma, we obtain t equals gamma tau naught, where t is the time measured in the ground frame and tau naught is the proper lifetime of the muon. Let us calculate. First, we derive gamma. Gamma is approximately 22.37 and t is 49.214 times 10 to the minus 6. Now let us calculate the flight distance of the muon as observed from the ground. Flight distance equals velocity of muon as observed from the ground times lifetime of muon as observed from the ground, approximately equals 14.7 kilometers. From the perspective of the ground observer, the muon generated at an altitude of 10 kilometers can easily reach the Earth's surface due to the time dilation effect of special relativity. The muon's lifetime did not merely appear to slow down, it actually slowed down. This is why the muon's lifetime was extended, and why it was actually observed at the Earth's surface. We have confirmed that muons are actually observed at the Earth's surface. However, from the muon's own perspective, the time required for the atmospheric layer to reach the muon is L naught over V approximately equals 33.4 times 10 to the minus 6 seconds. Since this is far longer than the muon's proper lifetime of tau naught equals 2.2 times 10 to the minus 6 seconds, the muon should decay before the 10 kilometers atmospheric layer reaches it. Yet whether viewed from the ground observer's perspective or from the muon's own perspective, the muon actually reaches the Earth's surface. This is where the effect of Lorentz contraction in special relativity comes into play. From the muon's own perspective, the distance of the Earth approaching it contracts. The muon's proper time remains tau naught, and the muon itself is at rest at the origin. The atmospheric layer with proper length L naught equals 10 kilometers approaches at velocity v. Due to Lorentz contraction, the thickness of the atmosphere through which the muon passes contracts to L equals L naught over gamma. Therefore, the condition for the muon to reach the surface is that it must travel through the contracted distance before its lifetime runs out. Tau naught is greater than or equal to L naught over gamma v. Proper lifetime is greater than or equal to contracted distance divided by velocity. Let us verify that this condition is satisfied. Here we calculate the arrival condition and verify whether it is satisfied. Please pause the video and work through it at your own pace. We have clarified from the muon's perspective why it is able to reach the Earth's surface through the effect of Lorentz contraction in special relativity. What this result tells us is that for the muon, the 10 kilometers wall is in reality only about 447 meters. If this were merely an apparent illusion, the muon would decay before reaching the ground. The fact that muons actually arrive at the Earth's surface is consistent with the predictions of special relativity. Experimental evidence from the muon experiment indicates that time dilation and Lorentz contraction are not merely appearances. They are actual physical phenomena.